Okay, in this little video, we're going to be talking about how to find the mean of a data set based upon the frequency table. Now remember, with frequency table, we wouldn't necessarily have all the data, so we can't find the exact mean. But if we don't have all the data and all we have is presented to us as a frequency table, this is the next best thing. Now, as I had mentioned before, there is a link here. We are linking back to our last chapter where we had talked about frequency tables and creating those, and then we're linking forward to as well to probability distributions that we'll talk about later, and we'll see that those are really just a frequency distribution that we had talked about through a frequency table. So first off, in order to find the mean, we need to find the midpoints. So remember, in finding a midpoint, if I want to find the midpoint of the per snatcher data based upon the frequency table that we had built, I am going to say 24 plus 16, and then I'm going to divide by 2. That's one way I could do this, right? And I can say, okay, well, this is going to give me 40, and then 40 divided by 2, which is going to give me 20. And then we can say plus 9 and plus 9 and plus 9, and we can get all those midpoints. So what we're going to end up with for our first class is going to be our midpoints here of 20. And then if I add 9, I'll get 29 for my second one. If I add 9 again, I'll get 38 for the next midpoint. And if I add 9 again, I'll get 47 for the last one. And that was the 4 that I would need. And this is for my classes, which are 16 to 24, and then 25 through 33, and then 34 through 42, and then 43 through 51. And from there, I also will need the frequency of these. Now these midpoints are what I'm going to call my x's, and the frequencies, I'm going to use this kind of scripty looking f. So the frequency in the first class was 3, the frequency in the second class was 4, the frequency in the third was 1, and the frequency in the last was 2 and then 1. And then the next thing I'm going to do is I'm going to multiply these together, x times f. So this is going to look like f times x. I'm going to put them in that order. So 3 times 20, which is 60, and 29 times 4. Sorry, my phone rang there. So 156 for 29 times 4, and then 38 times 2, which gives us 76, and then 47 times 1, which gives us 47. Now the next thing that I need is I need to add all of these up, and that will be the sum of the f times x's. And the sum of the f times x's is what we're going to use to find our mean. So we're going to have 60, and I'm just going to do this on the calculator, plus 156 plus 76 plus 47, and that's going to give us 339. And that is going to be our sum of our f of x's. And our x bar, based upon a frequency table, is the sum of the f of x's, f times x's, and that's going to be divided by the sample size, n. So we have our sum, which is 339, and then we divide it by the n, which was 10. Same n as before. Remember, the n we can find in a frequency table by adding up the frequencies. Those should add up to the sample size. And so what we find is our mean based upon the frequency table is 33.9 years. Now that does not agree with what the mean we just found for our per snatcher data, right? Well, remember, when we looked at the per snatcher data, what we saw was data that looked fairly skewed, right? We saw this from the shape of the distribution based upon a frequency histogram, which was based upon our frequency table. So finding the mean based upon a frequency table if we're looking at skewed data, isn't going to be necessarily all that accurate, because what this basically is saying is that there's pretty much the same amount of data in each, and each of those points are pretty well represented by the middle of the class. And as such, then we can find the mean based upon that single point. So basically what we're saying is there are 3 points in 16 to 24. And our assumption is that they're evenly enough distributed, so representing all 3 of them by 20 is a good representation. And likewise, representing all 3 of these by 29 is a good representation, so on and so forth. And therefore, this is never going to be 100% accurate unless this thing is really, really super symmetric data. And what we're seeing is it's quite a ways off there. We didn't even quite have 30, it was 29.8. So 33, almost 4 points off there. That's quite a substantial difference. So that, I expect you to know how to do that, and but not to replicate it for a test ever. So now it's time to start to talk about skewness. So remember before we talked about skewed data, and we talked about having this skew, and we talked about having this as fairly symmetric data, and then we talked about this. And we said these here and here were skewed, and we called this symmetric. Well, skewed data actually has a name attached to it, and we did talk about that a little bit, the fact that this one's called right skewed data and this one's called left skewed data. And it has nothing to do where the bump is, it has something to do with another measure. And that measure is actually the mean and the median and the mode, and how they're related to one another. And we're actually comparing the mean and the median to the mode. And when the mean and the median are to the left of the mode, then we're calling it left skewed data. And when the mean and the median are to the right of the mode, then we're calling it right skewed data. So this one, the right skewed, is the mode being over here, and then my mean and my median being over to this side. Now, sometimes the mean will be even further over than the median, and sometimes it won't. So you might think that you could gauge based upon those, but it's not necessarily a good measure. So this is what we call the right skewed. And another name for that is positively skewed data. Here in the symmetric data, the mean equals approximately the median, which is approximately equal to the mode. Now there's something that I would like to mention, that in truly perfect symmetric data, which we call normal data, there actually isn't a mode, in which case we couldn't really do this kind of an analysis. But in that case, we would have mean and a median that would be approximately equal. So we could go to those in that extreme. And then over in this one, where we have left skewed data, or negatively skewed data, in this case, the mean and the median, they're going to be on the left side of the mode. And that's what we call left skew. So you see this measure of left, and this is also sometimes called negatively skewed data. That is a measure of where the mean and the median are in comparison to the mode. And if we don't have a mode, that doesn't make too much sense. So those are our names that we had never really discussed before. So this is right skewed, left skewed, and then symmetric approximately. Now let's just summarize really quickly these 3 measures of center that we have had. First of all, the mode. The mode is a good measure of center for all types of data, both qualitative data and quantitative data. It is least informative for the quantitative data, and it is the only choice we have for nominal data, which is a qualitative type. Finally, the median, or next the median. The median is good for ordinal data, interval data, and ratio data. In other words, interval ratio, all types of quantitative data, and a little bit of qualitative data, the ordinal data. So it's the best choice for non-symmetric quantitative data, and it's the only real choice for ordinal data. So if we want a number kind of summary for ordinal data, this is really the only type that you could actually give. Now the mean is only available to us for interval and ratio. Remember that I told you in class that sociologists and psychologists sometimes will differ in opinion on this with statisticians. They will say, well, the mean's appropriate for the type of data that they refer to as a Likert scale, which is truly, in a statistician's eyes, a type of data that is ordinal. So the mean is really only available for quantitative data. It is the most common because most people understand what it is. It is what we like to talk about in statistics as an unbiased estimator, and its problem is that it's affected by outliers. It's not what we would call a resistant measure, and so because we may sometimes have this information that is causing a skew, the median sometimes is better than the mean as a measure, although it will never be unbiased. And so those are our measures of center, and that's where I'm going to wrap up this video.